Login accepted.
Welcome everyone. My name is Paweł Łoziński, and this talk will be about technical challenges of cloud-native, consolidated, globally distributed trade ledger. So let's get started. The agenda is to basically try to go through what are the business requirements, high-level business requirements that stand in front of such a system, like a trade ledger, what it actually is, what is the business that it needs to support. From the description of what that business is, we'll try to distill some main requirements for the system. We'll then go through some main system-level challenges that need to be addressed when someone constructs such a thing as trade ledger. And then we'll diverge into more technical part where I'll talk a little bit about Google Cloud Spanner as a database, and I'll explain why it might be a good fit for such a problem. We'll talk about what problems Spanner can solve for us out of the box, but then also mention some things that really aren't solved yet, right, and therefore needs to be addressed somehow. Obviously, this all is a bit of a simplification of the full problem, but I think the main parts will be there. If anyone would be interested in more detail, please reach out to me after the talk. I'll be available at the booth that Goldman Sachs has at the first floor, so I encourage you to come by and discuss. The clock isn't running. Can we fix this? Second. Okay, I'll use the personal clock for the time being. Okay, so let's dive into it. Short introduction to what trading is. It's not that I'm an expert myself, but I can definitely explain the gist of it and what are sort of the main properties of that business that are of interest to us. So when it comes to trading, we mainly associate it with the problem of buying and selling, right? And for us, consumers, what we often not realize is that we are on a market that can be referred to as a spot market. And the spot market is a market in which the only prices you have available to you are spot prices. So a price that is available at any given point in time for a given good or service that you can basically pay and get that for yourself, right? When we move to the business domain, this starts to be more complicated. And it starts to be more complicated for a reason, which I'll try to explain based on the following example. So imagine we have an airline that has a projected fuel consumption, right? And it knows that it will consume X number of gallons of fuel over a Y number of years, right? And so on the spot market, what that airline would do is it would actually need to purchase that fuel at any given point in time by the price that's actually available at that point in time in order to make the airplanes fly, right? Quite simply. Now, this introduces the risk for the airline because those prices may obviously go up and down, right? And if they move in the direction that's not advantageous for the airline, so in the case of oil, obviously, if the prices go up, then there is a risk of increased cost of operation for the airline, right? And that's something that a business of certain size just wishes to avoid somehow, right? And this is a simple example of why we may need to be able to trade things that are a bit more complex than basically a stock or basically a commodity at a spot price. And an example mentioned here is an oil future. So when a company enters into a contract with a bank, say, for an oil future, it enters into an agreement that it will purchase a certain amount of oil over certain periods of time by a certain price, right? And that price may differ from the actual price on the market. And if the company is able to enter into such an agreement with a bank, then it is able to offload the risk of the price going the wrong direction. So the main advantage for the company is to deal with the risk, and the advantage for the bank obviously is that it can make margin profits based on that kind of trading activity. So the basic terms that we are mentioning here is, well, the first, a bank has a desk. So if a company comes to a bank in order to do a trading, not necessarily a company, a person or anyone, any entity, then they would contact a desk. And that desk is a set of traders or sales people who basically are typically located in a given geographical location and are responsible for contacts with the outside world and entering into various types of agreements. Second, we've discussed that there is a contract. So a contract is this fully resolved legal obligation that binds two parties. A contract, before we get to a contract, we may actually have a sort of earlier form of an agreement, which is a deal. So a deal is something that's not fully specified yet, right? So for example, a client calls and orders a certain product by a certain price, the agreement is done, but there are some aspects of it that still needs to be tweaked, right? So this is a process in which we go from an initial deal to a contract or to a set of contracts that basically fulfill that deal. Furthermore, those contracts are subject to what's called aging. So as they are agreements that typically are long-lasted, they may last up to decades, they undergo this process of aging, which is to say that as time flies and as, for example, a given contract is fulfilled by delivering certain cash flows to certain parties, then some aspects of that contract change, right? And we have this process of aging over time. An important notion in banking is an asset. So an asset is something that a bank owns, either owns it by itself or on behalf of a customer. And an asset may be a contract itself, right? Or a fungible, which is to say that it's something that is traded in some quantities, right? Like stock or commodity. A balance is a set of assets that are aggregated according to some attributes. So a balance says that bank holds certain amount of assets that are, for example, grouped by their type, right? And the position is a single item of that balance, right? So a single position may say that a bank holds this number of contracts for FX swap on USD and Japanese yen. And an important activity that bank performs is risk management, right? Again, I'm not necessarily an expert on risk management. We do have experts on our booth if you wish to learn more. But essentially, risk management is about hedging. So hedging means that we're able to say that if a bank entered into, for example, a contract for this oil price, right? Then if a price that the bank agreed to is compared to the price on the market is a low price, right? Then someone needs to pay the difference, right? And therefore, there is a risk of sort of making losses on the bank side, which then needs to be compensated with some other mechanisms, right? And those other mechanisms typically involve trading some other products that allow entering into risks in a different direction, right? And the process of hedging is this process of being able to decompose what are the risks that a bank enters into and then trading appropriate products in order to mitigate those risks. So in the given example, a credit default swap is a particular product which means that is a contract that promises that a certain specific asset, for example, an amount of cash, will be paid if a specific event happens, right? For example, if the company with which the bank trades on oil, assuming some benefits from it, will default, right? So we'll go bankrupt. And that specific risk of an entity with which one trades going bankrupt is called a counterparty risk, right? And so this process of trading involves entering into various contracts with various entities that are based on different types of assets, right? Prices of those assets may go into different directions. And there is this art of actually maintaining a balance in order to not to enter into risks that are too high, right? And then may result in either high losses or even jeopardize existence of the financial institution itself. Another important aspect of bank's business is regulatory reporting. So this is any interactions with institutions that regulate banks' activities. And due to the sort of critical nature that banks fulfill in the industry, there's a number of regulations that those institutions, that banks need to fulfill, and those governmental institutions pose on them. An example mentioned here is a MiFID reporting, which is a requirement to report any over-the-counter contract within 15 minutes from when the trade happened, right? So imagine any given trade that the bank enters into, like for example the oil future, needs to be reported to the legal institution in the period of 15 minutes. And that's from when the trade is made to the point where the regulator is aware that that contract was made. On top of that, there's many different types of regulatory reporting, including ad hoc queries about certain contracts, certain deals that were made, and asks, for example, to provide further detail on specific trading activity. And so with that background, what is a ledger, right? So a ledger is a complete record of all relevant events, so contracts, deals, aging events that affect specific balances, right? So this is a system of record that basically keeps track of what happened, right? When it comes to financial obligations of the firm and how those obligations evolve, what basically happened and what is the current state. So example of queries that go against ledger would be, show me all books that a given desk trades, right? Or show me, for a given customer, all its accounts, all her accounts, right? For a given book, show me all open contracts that are on a given book, right? So for a given book, show me everything that's currently active, right? Or was active at a given point in time in the past. So a ledger system serves as a golden source of truth for the purpose of performing the trading activity, risk management of that activity, and there are sort of other middle office and back office functions that I won't be going into here. You may be aware of the term distributed trade ledger. So distributed trade ledger is a type of ledger, right? That sort of is constructed under certain assumptions, right? Those assumptions being that there is no single trusted party who can be the authoritative sort of source to the answer of what actually happened on the market or to the firm. And so there needs to be this distributed transaction log, right? Which the DTL maintains. More on financial products. So an oil future that I mentioned at the beginning is one of the simplest financial products that can be traded. Essentially, those products can get pretty large, and they may contain multiple different parameters that specify the exact shape of what actually was traded. Here on the left, you can see part of a description of an FX single leg, so a trade that is made on a pair of currencies. Again, a quite simple example. Those tend to go to really large sizes when it comes to more complicated financial products. So they can differ in shape and size. The definitions of those products may evolve over time. And so any structure like this shown on the left here may to some extent change as sort of conditions on the market evolve. New products can be defined. This is a business as usual operation. And for any given product, as we mentioned earlier, you need to be able to query the set of products that were traded by attributes that are somehow embedded in those structures, right? So you may ask yourself, where does the paper come in, right? So if there's a contract, obviously there needs to be some agreement that is signed by two parties. So essentially, in electronic trading, this is, for practical reasons, not always the case, right? What is being done is we operate on the level of those nested structures, right? The specified parameters of contracts. And out of those, the sort of paper agreement could be generated, right? But this is only the process of, sort of adding language to the parameters that are otherwise present in this nested structure here. Okay, so much for the business level introduction. If the ledger is a system that needs to be able to tell sort of what happened when it comes to this activity, right? That, as we said, may be quite complex and evolves over time, and has those products have different shapes, right? We may need to answer questions on products that were traded at some point in the past. So what can we distill out of this description in terms of requirements, right? So first of all, we need to be able to support an ever-growing data set of contracts, okay? Because the trading activity goes on, right? And it's not the case that we can somehow dispose of the old activity. We at least need a way to somehow reference it, right? And preferably in a way that's not too slow for us to be able to respond to, for example, the regulatory inquiries. Then we need to be able to maintain an up-to-date view of the positions, right? So the question of what are the current open contracts is the very important question that the ledger needs to be able to answer. On top of that, a historical view of those positions. So what contracts were opened at some point in time in the past, right? The flexibility of shape is important. The requirement the possibility to stream ongoing activity that happens in the ledger is also important, for example, in the context of the MiFID II reporting. And then high resiliency, right? So for systems that underpin trading activity of a bank like Goldman Sachs, undergo significant scrutiny when it comes to their ability to actually operate, right? And there's processes that are called business continuity planning, where there's analysis that being made, sort of what would happen if a given type of failure would occur in the system, right? And would that system still be able to operate? If not, what needs to happen for it to be able to operate? So the resiliency is sort of critical, as you'd imagine, right? Because when it comes to, well, the volume of trading, but also the value of trading that may go into millions of dollars, right? The question of, is the system capable of operating smoothly is the critical one. Something I didn't mention when talking about desks. So desks are things that are located geographically, right? So you have a set of traders that trade in a given desk, specifically in a given geographical location. This is how you, for example, determine what are the legal obligations that relate to the contracts in which a bank participates, right? These are the legal obligations typically of the regulator of the country in which the desk is located. Some exceptions may apply, but that's a general rule. But that's not to say that the trading data is always local, right? Because in the global trading business, essentially, trading across different countries is not an uncommon operation, right? And so global availability of the data set is also critical. So what are the system level challenges that we would expect? Obviously, this is not a full list, but when it comes to basically persisting the data, we may expect the following, that if we were to go with a single node database, right, where we plug in a messaging system and we have a distributed transaction between the two, right, then obviously we have scaling limitations, right, because any single node database has capacity limits, and therefore we need to enter into some application level sharding and then application level management of resiliency, right? Because if we have a node failure, then some portion of our data set is made unavailable, and then there's a question, how do we make it available again, right? If we would go with distributed database that, for example, lacks transactional support, then we enter into the risk of data inconsistency, and that's, if you imagine, quite a critical problem, right? Because if we, for example, compute a balance sheet, right, and we are off by, I don't know, 7 million yen, right, then there's a question, why that's the case, right? And that kind of question is something that sort of keeps designers of such systems awake at night, right? So not an option, really. If we were to go with a cluster database, or a clustered messaging system like Kafka, right? Cluster database, basically also you name it, right? Spanner, HBase, Cassandra, all of those lack the support of a distributed transaction, right? And that's something that is actually an important limitation, right? As soon as you go into the cluster solution, which we want, right? Because they offer scalability basically, either on the level of the storage or on the level of messaging. We still need to maintain consistency between various components of a system that uses those. And we actually have no easy way to do that, that we used to have when it came to traditional relational databases and messaging queues. And again, the problem of inconsistency comes into play, and that's the problem that we're mainly trying to avoid when designing a ledger. What we could be doing is, if we store data in a cluster database, right, we can just do sort of some time-based polling for this data in order to pull it out in consistent manner. But that introduces some scaling limitations, because this is basically limited to the efficiency of that time-based polling. And then finally, a relational model, which is the sort of typical model in which we think about this data, has its limitations because of just the richness of the models of financial data that we are dealing with, right? At least a relational model that is just baked into the database statically just imposes limitations that may be difficult to overcome, because essentially, how do you evolve such a schema, right, as your products evolve? Right, so now quick switch to a potential solution. So there's a ton of material of what Google Spanner is. I chose some graphic referenced here, which I think is nice. I don't think I'll go through all of this, but just to give you an idea. So Cloud Spanner is a distributed database that's deployed across different nodes, and those nodes are being deployed into different zones, right? So if you can see the green box here, we have an example of a database that spans across 4 nodes, and those 4 nodes have 3 copies in 3 zones that are located in a single region, right? And this is what creates a single region instance of Spanner. Within this instance, so we may have regional instance, we may also have multi-region instances, but in a given Spanner instance, if we define a table and persist data to it, then this data is being distributed based on the primary key, and it's being distributed by the virtue of splitting the space of the primary key into partitions. And those partitions, here we have term splits. Those partitions are basically distributed across different nodes of the spanner database, and each partition has a resiliency mechanism where it has a leader and it has a sort of following nodes that basically maintain copies of that partition. Another important aspect is that we actually have a external consistency of the data that we store in the database that's achieved due to the true time technology that Spanner uses, right? So we actually have a global notion of time, and external consistency means that when we persist data to Spanner and we read it out of Spanner, we are never in a situation where we've read the data at a certain point in time, but this read is not complete, right? So there would have been records that were persisted with earlier timestamp, but somehow due to, for example, a long-running transaction, we didn't observe them in the read that we did, right? And therefore we may have an inconsistent view of what was actually persisted to the database. And that's probably basically it. There's much more to Spanner, so I encourage you to read about it, but for the purpose of our discussion, essentially we have a distributed database that provides resiliency, that provides scalability, and that provides the consistency guarantees that we would be interested in, right? So it seems like a nice fit in the context of the discussion that I've just went through. When it comes to pulling data out of such a database, if we were in an on-prem setup, right, and we didn't want to do any time-based polling of data, there is a typical pattern of actually reading the ongoing activity in a database that's called change data capture. You may have heard of it. And this is essentially a technique in which you can tail a transaction log and export everything that's being persisted to the database to, for example, Kafka, right, or some other storage of your choice. That type of setup is unfortunately not available in a cloud-native environment, right, because then you actually don't have access to the database, and so you actually made a conscious choice not to have that access, right, because you wish to not to deal with the operational issues that come with actually sort of hosting the database yourself, right? But if you want the cloud provider to do that, then you have no easy way of actually plugging into that transaction log, right, and perform the scanning of the ongoing activity. So here, the solution that Spanner has is called change streams, where it is sort of implementation of that pattern, but natively in the database. So in this mechanism, on the left shown here, you have partitions. Partitions essentially have their life cycles. So a single partition may, for example, be moved from one node to another. That is to say that the leader of the partition was moved to one node to another. It may be split, right? So if we perform insertions into a given key range, and this number of insertions exceeds a certain threshold, this partition is being split into two. And those two partitions are then managed independently. And subsequently, if there are deletes from data from the table, then there may be a decision made automatically by Spanner to merge two partitions into one. And this is a life cycle of a partition, which is followed by the change streams mechanism. So the change stream mechanisms is the picture on the right here. We have a node. A given node holds certain splits of the table in Spanner database. Those splits are being duplicated into what is called change splits. And those change splits are basically logs of changes that can be read via SQL-like syntax that's shown below here. And this is basically querying the stream of changes that were persisted to those sort of little change logs on those nodes, right? And obviously, this gets a bit complicated when we have this evolution of partitions. And so in the select statements themselves, what you need to specify is you need to specify the timestamps from which that sort of define the range from which you wish to read, and you need to specify partition tokens so these are sort of names of the partitions that you wish to read, right? And in the response to such a query, you may receive actually more partition tokens, right? Which means that a given partition that you were trying to read got split, and now you need to read those new partitions that you received as a response to your query. So it's not like a, let's say, an ideal solution because you still need to have the complexity of managing those partition tokens, right? But at least you're able to consistently read the changes as they happen to the database without the necessity of time-based polling, which also is a nice property of the database. So with that, how do we do with the requirements that we mentioned at the beginning? We do have the support for ever-growing dataset, right? Because Spanner scales linearly, and it's an actually business-as-usual operation in order to increase its capacity. We're able to maintain an up-to-date view of the positions. So the currently open contracts problem. The historical view is also to some extent supported because what Google Spanner has is it has this PATR functionality where you're actually able to read a table at a point in time that you can specify in the past, and you can perform what's called a stale read at a given point in time in the past, and you can then receive a consistent snapshot of that data at that point in time. The caveat mentioned here is that this mechanism has a time limitation, so you can actually now specify up to 7 days of such retention. To go beyond that, you basically need either to change your model of the data, or you need some way of exporting of those positional views into some different type of storage, right? But we sort of don't have time to go to the details here. When it comes to the flexible storage of documents, it's not that easy, right? With the relational model that Spanner supports. Spanner actually has a JSON type, right? So you're able to specify a type of a column that is JSON. And further to that, you can specify also generated columns. So you can say that you have a column in your Spanner table that is defined by a JSON path, and everything that all the documents that get persisted to that table basically undergo an extraction where you take out what's persisted under the given JSON path and you store it in the generated column, right? That mechanism has two limitations, mainly. One is that this mechanism works only for one-to-one relationship, so it only works if you're extracting one thing out of this JSON document persisted in the JSON column. And the other is that you're actually embedding the structure of the JSON in the schema itself then, right? Because you're actually, in your DDL, you need to specify what are the JSON paths in which you're interested, and evolution of that becomes tricky. An efficient way of streaming ongoing activity is there, right? Although with a caveat that typically for a ledger system, we're not only interested in streaming of all the events that occurred in the ledger, we're also interested in the ordering, so partial ordering of those events according to some attribute, right? In order to capture evolutions of, for example, state of a given contract, right? And this doesn't come out of the box with change streams because for change streams, the partition space may be split at arbitrary points in time in arbitrary places, right? And therefore you may persist records into different partitions, which are then being sort of tailed individually, and the order between those isn't guaranteed yet, right? But there are also ways to deal with that. High resiliency is supported out of the box, right? So as mentioned, you may have single region instances, you may have multi-region instances, and actually the latency penalty that you pay when going from single region to multi-region is at the level of 12 milliseconds. So quite attractive in order to be able to sort of achieve the resiliency that is needed in this type of systems. And global availability of data, again, is there. What's available is sort of regions that are located in US, in Europe, in Asia, and sort of instances that span on multiple of those regions are also sort of made available by Google. So basically, we may tick the box there, right? You may feel cheated to some extent here, right? Because when we discuss such a sort of critical and elaborate system as a ledger, why do we say then if we just choose a database, right, then we basically tick off many of the boxes that we wanted to tick off when it comes to requirements, right? But that's the trick, sort of with the level of criticality of such a system, you do want to have as simple architecture as possible that supports it, right? Because essentially the more moving parts you have, the more places there are where some failure may occur, right? And some inconsistency may occur. So if you're able to deliver such a system with basically a single database, then it's not a bad choice as long as that database is a good fit. So lastly, the point that we said is not covered yet, right? So what about this versatile data set that can be expressed with those elaborate JSON structures? How do we actually go about sort of efficiently, well, not efficiently, mainly sustainably managing it, right? So how do we actually persist this data and query this data in a way that we can actually manage with those evolving models and those rich structures? So this problem has many potential answers. I don't claim to present sort of the only possible one, but one way to address it is the following. So let's say that we don't deal with the complexity of the internal structure of the financial products in the physical schema itself, right? So the physical schema that you have shown here is quite simple. We basically capture recognition units, so the things that hold the definitions of the products and contracts themselves, and we hold some state that relate to those contracts in a separate table, right? So let's imagine that we have a very simple physical database schema, which gives us still all the advantages of resiliency and scalability and retrieval of data that we've mentioned before, but we just encapsulate the complexity of the internal structures. So what we may define on top of that is a logical view. And that logical view, if we add all the relationships that can occur between the financial products for a given sort of state of a contract, that's called economic subheader here, then we get such a picture. And here we still have a relational model, right? But this is a model that doesn't physically exist in a database, right? And advantage of this approach is you're actually able to sort of express in a relational way this sort of vast number of different parameters that pertain to the financial data, right? But you don't embed that physically into a model, into a database, right? And then if you do that, what you basically need is the translation between the logical model and the physical model. And as long as you have that, using a query engine, for example, then you're able to sort of perform queries against the logical view and leverage the fact that the logical relational schema that you have is much richer than the physical one. And so what you're able to specify on top of the logical view and what is done in one of the systems that I describe here is that based on that logical view that already incorporates this complexity of internal structures of financial products, we're able to define a DSL, right, that basically, well, captures that structure in a language that we're able then to use in order to construct queries, right? And here what you have shown is multiple different types of queries that basically are expressed in the language of that logical, more complex, more elaborate view. Yes. So okay, let's say we do have a rich query, right? We have a SQL query that sort of is expressed in this fine-grained terms that we wanted to have, right? We now need a way to translate that query into the simpler query that we will actually execute against the spanner database, right? What are the techniques that we have at our disposal to do that? We basically can leverage two techniques that are sort of typical in the area of query optimization, which is called projection and filter pushdown. And so for any given query expressed here, the sort of top level view presented here is what's called the logical view of logical execution plan of a query, which expresses the SQL almost literally, right? And then the one below is a physical logical plan of a query where the logical one is being transposed into a different form, right? And the two techniques mentioned here mean that we basically push down any conditions that we expressed here, and we push down the projection that we've expressed here to a lower level, right? And so this is actually visible here, right? So the query was translated in such a way that we've pushed down the predicate on attribute 4, right? And attribute 4 is one specified here, 0, 1, 2, 3, 4, an SBH node. And what we are projecting out is this set of columns, right? And now if this is all done in a query engine that sits on top of actual spanner database, right, then the table that is being queried here is actually, in this case, a Java class, right? Because the query engine of use here is called Apache Calcite. And the table that actually implements, quote unquote, this thing here is basically Java code that somehow translates what is being expressed here into queries to the underlying storage where we can basically efficiently pull out data using this translation. What further comes on top of that, right, is that if you say that you're specifying a logical view of data that is rich and allows you to model whatever you need to model in your system, you not necessarily want to expose a query engine to your consumers, right? Because essentially then you're entering into all of the problems that relate to the fact that against a query engine, you can specify an arbitrary query, and then those queries may translate into different query plans, and all of that need to be supported in an efficient way, right? So how you can deal with that, you can basically define an API layer on top, right? And if you have a logical relational view that you already have modeled, what you can do is you can generate an API out of that, right? And this is the thing that you can actually expose to your clients. Because essentially, this is the thing that allows you to have a well-defined contract between the consumer of the data and what it is that you actually do in order to retrieve the data efficiently out of the underlying storage. And the example of such a translation is shown here, where we're going from the relational schema specified in Apache Calcite into the definition of services on a gRPC layer used in this kind of system. And with that, we basically summarize. So this talk was an attempt to go through what a trade ledger actually is, right? And what is the purpose it serves in a bank. We've discussed how transactional, We've discussed how transactional, externally consistent distributed database helps building it, right? Again, with the caveat that you actually do want to have as little problems as possible with such a system. So an architecture that's as simple as possible, potentially just a single database, is something that is actually a good fit. But you shouldn't expect that this is an architecture that solves all your problems, obviously, right? And therefore you need this additional layer of dealing with whatever your database is not capable of dealing with. And here what we've discussed is this approach to actually introduce a logical relational schema that sits on top of the physical one, right? That does any additional modeling that you wish to do, and that is capable of supporting the requirements of being able to evolve that view without friction, without actually physically changing the schema of the database. And how such an approach can allow you to flexibly model your data set that you persist in your ledger, and still do that in a business agnostic way without actually hard coding what it is that you actually process in the ledger system. This further allows you to decouple the querying logic, right? So the queries that were mentioned here, since they are not queries executed against the physical database, you actually have choices about how you go about realizing them against the schema that you have, right? And if you're able to do that, then you're able to basically evolve whatever you have underneath. And you can do that without actually breaking the contracts that you've entered into on the higher level, which gives you the sustainability. And lastly, since exposing a query engine is typically a dangerous operation, right? As a systems integration pattern, what you would rather do is you'd rather define a DSL, and you'd rather translate that DSL into actually statically typed public API, right? That can be generated but still need to be fixed somehow. And it's that public API that you commit to support, not the underlying query engine structure. And that's basically that. We have some time for questions, if there are any.
In real life, how do you handle the storage of data that is older than 7 days?
Yes, good question. So essentially, this is something that is another thing that you don't get free out of the database itself, right? So this positional view of the data is what's important about it is that it actually evolves over time, right? So you actually add things to there and you remove things from there. If you want to go beyond what Spanner gives you out of the box, you have basically two choices. You can, when you query your positional views with some historical timestamps, you can export the results of those queries to, for example, in the context of Google Cloud Platform, a BigQuery engine, right? And they perform analytical type of queries on the historical data, which typically is fine as typically queries related to history come with lower latency requirements than queries that relate to what happens now, right? And your other option is to leverage different modeling techniques, like, for example, bitemporal milestoning, in order to be able to basically maintain the history on the level of the physical schema of the database, right? And then you sort of don't leverage Spanner's functionality to do historical queries for you. You, for example, sacrifice the property of immutability of the data, right? Because you essentially need to modify the timestamps yourselves then. But if you do that, then you're basically not bound by any limitation when it comes to retention that Spanner has. Do we have any other questions? If not, then thank you very much. And again, if anything comes to your mind, I'm available at first floor at the Goldman Sachs booth. Thank you.